so I'm gonna really just talk about the developments in the last 2 years, from basically predominantly transport data, which we had taken in our group, and I will really touch base on the superconducting correlated and magnetic phases which we observe in our twisted bilayer graphene devices. And first of all, I want to thank the group. So the work was done predominantly by postdoc Xiaobo, Peter Stepanov, and MC Tedes. And I'm also very grateful for theory collaborations by Alan McDonald, Andrew Bernabet, Dmitri Efetov. And really just okay, I didn't know exactly what the sort of background of the people who are attending going to be, but I wanted to give like a 10 to 15 minute introduction to moraine materials and twisted bilayer graphene and to flat band physics, etc. Then I will predominantly talk about the transport results from our own group, and really mostly concentrate on the superconducting and the correlated insulator phases. And really, just to start very slow, so I think the field of graphene really exists for now 15 years. However, from the very beginning, from the time when Andrei Geim and Kostya Novoselov extracted graphene, people were really wondering whether this exceptional material can also host interacting electron phases. And really, I think until 2 or 3 years ago, graphene was rather poor on these phases. So mostly everything was described as a single particle picture. However, of course, there were a lot of predictions early on. And then, of course, the big breakthrough came by Pablo Herrero now 3 years ago, where he reported that in a new type of graphene called twisted bilayer graphene, where 2 sheets of carbon are basically rotated with respect to one another, he observed signatures of correlated insulators, and he also reported on superconductivity flanking these phases. And then this was still not it. So there were a year later, the groups of David Goldhammer-Borden and Andrea Young, they also reported that the system also contains magnetic phases and also topological phases. Basically, they observed an almost quantum Hall effect. And we're really quite excited to be in the field. And I also want to mention one of the really special things about this material is also that all these phases are kind of living in the same device and are gate tunable between one another. So one can actually have an extremely high level of control, and one can tune between these phases up and down. And this, of course, allows new types of sort of experiments which can be performed. And really, to go sort of very slow into that field. So really, I wanted to just to give a little bit of overview what happened the years before this discovery. And again, it all started by the extraction of graphene. So in the group of Andrei Geim, people realized that they can extract perfectly two-dimensional crystals from bulk crystals if you do it in a van der Waals material. And they were able to sort of extract single layers of graphene and deposit it on silicon oxide substrates. Then, of course, for the years, people have learned to do this with many other materials. So prominently hexagonal boron nitride, which is an insulator. People learned to extract single layers as well. And then also this happened mostly at Columbia when I was there by groups of Philip Kim, Jim Hohen, and Corey Dean were involved in this. People also learned to make these, to stamp these two-dimensional material on top of one another and to sort of assemble them vertically in these designer van der Waals stacks. And so the surprise here was that the interfaces formed by this sort of rather rude technique were still extremely good. So really, if you look at typical transmission electron microscopy images between hexagonal boron nitride, graphene, and LS2, you see that the interfaces are extremely good. And what is also very special is that you can align the crystallographic orientations between the different layers, and you can form these so-called Murray superlattices, which I will talk in a second about. And really, I want to contrast this these heterostructures made by van der Waals materials to heterostructures that were traditionally grown throughout the years and decades before that. And really, the difference is here that we do not start with single atom species, which we sprinkle onto substrates. So like in molecular beam epitaxy, in these techniques, because you start with single atoms, you kind of guarantee that these atoms, when they hit a particular surface, they align to the crystallographic orientation of that particular surface. So you cannot orient the crystallographic orientation; they're all kind of pointing in the same direction. And really, because in these van der Waals heterostructures, we start with already preformed two-dimensional crystals, we can actually align them with any given orientation. And basically, this is a really new and exciting capability of these van der Waals heterostructures. And to highlight what's really going on in the physics when we do this twisting, so I want to start just basically with a single sheet of graphene. This is again this just two-dimensional hexagonal lattice of atoms. If we do tight binding calculations, we just get this rock cone dispersion, which is basically defined which is basically a result of those two equivalent carbon atoms in the unit cell and a gamma zero term, which allows hopping between these lattice sites. Then really what dramatically changes if we look at AB bilayer graphene. So this is the sort of the typical naturally occurring form of graphene, where really one layer sits just on top of the other layer of graphene. And here now, because we have these extra tunneling terms between the layers, the band structure becomes dramatically renormalized, and really the band structure at charge neutrality is not anymore linear, but it has this parabolic dispersion relation. So basically, really these tunneling terms, they have a strong effect on the band structure. And of course, now if we start rotating these layers one on top of another, these hopping terms are not anymore a good sort of, they're not fixed for the whole device, but they're changing periodically with this Murray lattice, which is created between the atoms. And really, so we can find, if we analyze this Murray potential, we will find regions where we have AA stacking of graphite, where really the carbon atoms just are directly one on top of another. And then if we sort of move away from these AA points, and we find regions of AB stacked graphene where the top and bottom layer are slightly shifted with respect to one another. And all of this sort of induces different tunneling terms between the layers, and really all of this can dramatically renormalize the band structure in the system. And just to give like some experimental sort of indications, sort of early on indications of the system as such. So first of all, really these Murray lattices are robust, so we can image them with scanning probe techniques. So for example, this is an image done by our collaborators Milan Allen in Leiden, and they were able to just image with STM and resolve a really periodic Murray superpotential. So all of these sort of periodic dots here, which you see, they're not single atoms, but those are really these Murray lattice sites. And secondly, so as I mentioned, so the band structure becomes really strongly renormalized when we go close to this so-called magic angle of 1.1 degrees. So here I show the theoretical band structure of twisted bilayer graphene if we consider a twist angle of 1.3 degrees. And what's really striking is, of course, the Fermi surface gets extremely complicated, but also the bands basically break up into different sections, and specifically at zero energy, we get these ultra-flat bands, which are separated by band gaps to higher order bands. And really, this can be seen in nano-orbits. So this is, for example, experiments done by our collaborators Felix Baumberger in Geneva. And really, we can see those ultra-bright flat bands and also energy gaps forming to higher order bands. And really, so basically, I think for the remainder of the talk, so the system which we're really looking at, and when we try to understand our experiments, we really try to look at a sort of this magic and graphene band structure where we have these ultra-flat bands of around 10 MeV bandwidth, which are isolated by larger band gaps to to dispersive bands at higher energies. And because these bands are so flat, the kinetic energy is almost zero for the electrons, and they basically stop moving and lock into place. And of course, also this means because kinetic energy is quenched, that interactions take over the physics of here. And also, what I also want to mention is, and I will come back later on in a little bit more detail to that. Also, these flat bands are now found to be topologically non-trivial. So because the newly formed Brilliant zones have winding numbers which are non-zero, it is basically impossible to find localized linear function solutions for the orbitals here. And really, basically, one has to think of these bands as kind of a sum of Chern bands, which have different Chern numbers, and we'll talk about this later on as well. So let me start just with the experiment. So really, the experiment which we're doing are relatively, I mean, once we have the device, the experiment is not actually so difficult. So we just measure resistance as a function of carrier density, and basically we basically sweep the Fermi energy from a completely empty Moiré band, and we sweep the Fermi energy through it until we completely fill it. And so basically, as you see, so the carrier density changes orders of magnitude if we do so. So first of all, when we start in this sort of lower energy gap, we find this robust insulating state. Also, when we completely fill the band structure, we find an energy gap. In the middle, we of course see this charge neutrality point. But as you can see, so there are many other features here in the system which are not defined by this single particle band structure, which I showed before. And in particular, those are these correlated insulating states, which appear at exactly integer filling of electrons per Moiré unit cell. So basically, exactly when we fill 1 electron, 2 electrons, or 3 electrons into the system. And these features, they're, again, not explained by a single particle picture, but they're really much better explained by sort of a naive assumption that we deal here with a mod-insulated picture, where really electrons like to localize at different lattice sites, and where kinetic energy is given just by the hopping term between neighboring lattice sites. And of course, also we need to consider the Coulomb energy, which kind of prohibits or makes it unfavorable for 2 electrons to sit in a single lattice site. So in that picture, of course, if really U is much bigger than T, and we deal with a fully occupied lattice site, so we have integer numbers of electrons per lattice site, then of course we form energy gaps, and we polarize the bands with respect to this energy gap. And I also want to mention, so I mentioned this before, so in graphene we have a fourfold degeneracy, so we have electrons, we have spins and value degrees of freedom. So in principle, whenever we polarize the bands and form an energy, a mod gap here, We also, of course, create some sort of symmetry in the problem. So we in principle can polarize the system with respect to value or with respect to spin, and form basically some sort of ferromagnetic states in this SU4 phase space, which is given by Valiant spin. And I will touch base about this much later. And then the other thing, of course, which was very striking, which was observed in the very beginning by Pablo, was that really when you sort of look at the temperature dependence of these resistance measurements, there are also regions where resistance just drops to zero. And this is shown here. So basically red are regions of high resistance and blue are regions of low resistance. So basically the insulators I talked to about a second ago are these red regions. And you can see flanking these red regions, there are a lot of blue regions where superconducting domes are observed. And the way we sort of characterize those superconductors are typically by doing all the sort of checks and balances one needs to consider here. So first of all, we really observe a zero resistance state. So resistance goes to zero. And if we look at, for example, the temperature dependence of the resistance here, we really can clearly define a TC. And TC in the system is typically in the orders of few Kelvin. Then, of course, we can apply a critical magnetic field, and we can see that these superconducting states disappear again, and we can define a critical magnetic field, which is in the orders of hundreds of millitesla. Of course, we observe also nonlinear conductance and critical currents in the system here. And again, here, critical currents are in the orders of 10 to 100 nanoamps. And I think so far, really, the smoking gun evidence, which really leaves little room for alternative interpretations, really, that in most devices we observe Fraunhofer interference patterns. So we have like really coherent Josephson junction coupling in the device if there's a weak link created somewhere that interrupts the superconductor. And here, from these measurements, we can, and actually from magnetic field measurements, we can extract also the coherence length of the superconductor, which is usually in the order of 15 nanometers. So it's in the order of several lattice constants of the Moray. Okay, and really, I think this superconducting state created probably the most excitement. So really, the excitement came from several kind of peculiarities of this superconductor. So first of all, it's the thinnest possible superconductor. So you can, I mean, there's really, it holds the record for the thinnest superconductor. It's 0.6 nanometers only in thickness. So this is basically showing thickness of various different superconductors. So magic and graphene is really at the bottom here. And then also it is by far the lowest carrier density superconductor. So the superconducting state basically is formed from a very low carrier density of electrons. And really this shows, this graph here, this axis shows the carrier density here. And you can see, so the carrier density of magic and graphene is, for example, 3 orders of magnitude lower than visco or the stellanite. So it's really special just by the sort of numbers it has. However, TC here is not so low, actually. TC is still really sizable. So I think the highest TC we observed so far was 5 Kelvin. And really, if one looks at the sort of TC ratio and the Fermi temperature ratio, it's really extremely high, and it's really only comparable to otherwise only comparable to cuprate superconductors. It's orders of magnitude larger than conventional superconductors like aluminum or niobium. And of course, last but not least, of course, what caught also a lot of attention is the phase diagram which kind of, naively looks also very similar to the cuprates, where again, we observe superconducting domes upon doping of correlated insulator phases.
Dmitri,
yep.
Do you have any estimation of the value of the U from experiments? Because this will also allow you to distinguish between this MOTEC scenario and other alternatives.
Right, exactly. So, okay, from transport, we cannot really directly measure U, but I think from STM, Sali Asdani, he reports 25 MeV for the U.
Mm-hmm.
Sorry, Dmitri, this is Antoine. So in connection with Angel's question, there is U, but there is also longer range Coulomb, right? So what do we know about how fast in space is the Coulomb interaction screened here?
Mm-hmm.
Or the screening length, if you want.
Right. I think. Okay. I wanted to talk about screening in a second, but we actually will talk about. We'll actually talk not about in-plane screening. Okay, so that's a good question. So I think I'll come back there. But I will talk not about in-plane screening, but I will talk out-of-plane screening. But in-plane screen, I'm not exactly sure right now, but it could be several lattice constants actually. I think it's not so quick, but I'm not 100% sure, to be honest.
So the Hubbard model is a good thing to have in mind, but it's probably not a realistic, quite realistic description.
I also want to mention, so what I presented before was kind of like a toy model for us to start thinking about the problem. And of course, it's not like a detailed model what you want to assume here in the system. It's just really an introductory sort of toy model. Yeah.
Sure. Thank you.
So obviously, for somebody who's working on the Hubbard model, this is not meant to be as simple.
No, also because I think it's building on this question also the long range screening, which I think is important, and also the ratio of U and T, because the T in this case is also not much smaller than the U.
Right.
20 millivs and the other is 10.
Right, exactly, yeah.
Okay, just okay, please go ahead.
Yeah, right, and so and actually this brings me also to the next point. So basically, I think what I wanted to talk about next is really the control of U versus T. So I think you mentioned the details. Maybe U and T are not actually that far off, but I think I want to emphasize that also here we have entirely new capabilities to control these parameters. And I really want to kind of compare again how special the system is, because it's really sits exactly in the intermediate sort of length scales compared to crystals and compared to optical lattices. And the specialty here is really that they're really, as I will explain in a second, there are really new ways to manipulate the system because really the lattice constant here is 10 nanometers and not angstroms like in cuprates, like crystals, or it's not microns like in optical lattices. So they're really new type of manipulations which we can perform if we assume this novel length scale. Really, this plays a huge role if we now start considering the details of the devices which we make. And again, I'll come back just for analogy to the simplistic Hubbard model here. And I really just wanted to mention that really all these parameters like T and U, they're not fixed in our problem. So first of all, T is a tunable parameter. So T is a function of twist angle. So that on magic angle, T is of course the lowest. So T is has a minimal. But whenever we go slightly away from the magic angle, T becomes much bigger. So the bandwidth of a 1.2 degree twisted bilayer graphene device is already 10 times bigger. So it's already like more like 100 MeV. So we can really accurately control T by just slightly changing the twist angle, but also we can really control U in the problem. So because, as I mentioned, so our devices are actually in a very embedded into a very non-trivial dielectric environment. So they're usually the twisted bilayer is encapsulated by HBN, which has a certain dielectric constant, but in principle, we can change that dielectric constant. And second of all, we usually have metallic gates close by to the plane of the magic and graphene. So as I will show in a second, so we have typically graphite gates or gold gates, which are sitting very close, which we typically use to control the carrier density. But also, these graphite gates are really just a few nanometers away. So we can, in principle, use these graphite gates to screen out interactions out of plane. And really, so basically, really the message here is that U versus T is a tuning parameter here. So we can control both T and U separately. And and again, so this is some calculations which Dmitri Efetov has done for us. This doesn't assume next and nearest neighbor screening. So really just next neighbor screening assumed here. But we were really wondering how U is affected by this metallic layer, which is only a few nanometers away from it. And really, we were wondering what is the length scale? How closely can we bring this metallic graphite gate to the magic and graphene such that the screening affects the U in a more pronounced way? And this is the calculation by Leonard. So here he calculates just U as a function of this gate distance. And really for above like 30 nanometer distance, we really don't observe any change. But with a length scale of around sort of characteristic length scale below 15 nanometers, U becomes really dramatically screened out. And this length scale, 15 nanometers, is really just the size of this Vanya function in the magic and graphene. So this is just the size of the meridian itself. And therefore, really this intermediate length scale, so that we deal here with a system where the lattice constant is much bigger than in typical crystals. This allows us kind of new tricks and manipulations that we can perform here. And I just sort of want to mention our experiment, which we performed here. So we really
just in the previous slide, yes. If I take this argument of how the U is screened by the graphene layer underneath, which is metallic, then if I do gating, basically you increase also the metallicity of the graphene layer. Then you would expect the U also change with the gating that you apply.
Yes, absolutely. So absolutely, yeah.
Okay.
So so I will mention this in a second. There is a follow-up experiment after our work came out by GLE and Brown University, and they used this tunability effect. So they were able to sort of charge the graphite gate and discharge it, effectively tuning the screening of the graphite gate, and they were able to see in a much more controlled way how the screening really affects it.
Okay.
And really, in a nutshell, so I mean, before GLE did this experiment, we did ours where we really, in a less controlled way, we really just made a bunch of devices with different twist angles and different dielectric thicknesses. And really, we cannot in these experiments completely distinguish what's more important, the screening or the sort of the band structure effect. We cannot completely disentangle it. But what's true is that in devices where twist angle is dead on magic angle and where the dielectric thickness is not that thin yet, we really see strong correlated insulators. We really do see strong correlated insulators. And in the devices where, again, the parameters were shifted, where where the kinetic energy is enhanced, and also where the dielectric screening is relatively strong, we don't see correlated insulators. So somehow really this proves the point that the correlated insulators can be quenched with these manipulations. And then in the work of GLE, again, he was able really to show in the same device, really by changing this sort of tunable screening layer, he was able to show that this is really, that the correlated insulators are strongly affected by the screening. And then,
Dmitri, this is very, very interesting, this tunability of the screening by gating. So my question is, what is the direct experimental probe that one actually is changing the in-layer screening? And is there any way to actually measure this directly? And, you know, this curve of U versus gate or something that you were showing, this is presumably a theory curve, or what is this?
In what we measure in transport, we can only measure temperature activation of some sort of energy gap. So this is always underestimating the sort of the gap which is performed. Really, in my experiments here, we only could extract the gap in an unscreened device, and we can try to extract the gap through temperature activation in a screen device.
I see.
But this is rather rough. What Ali Yazdani, so I know that Ali Yazdani is also trying to look at these screen devices. They can, of course, be much more, with SEM, they can extract these gaps in a much more controlled way. Mm-hmm. I think we're really early on in these experiments. I think there are more detailed experiments which will happen.
Okay.
Hi, I also have a question here. So we can see in the first picture that the superconducting dome is also increasing as we decrease the thickness. And what do you think, is the reason for that? Is it because the correlated insulator decrease and superconducting increase?
So it seems that indeed, like in this curve here, you would expect a correlated insulator in the middle here of the superconducting dome. And it seems that indeed, once the correlated insulator disappears, the superconductivity takes over that phase space where the correlated insulator appeared. Right, and then of course, I guess the other part of your question is, what does it mean? Why does it? So there seems to be a competition between the insulating phase and the superconducting phase. And I think this is still a debate what it means. I think I heard different arguments. Of course, one argument could be that it's really just, I mean, if you look at this, whenever sort of the insulator disappears, the correlation don't disappear. So it's just like really that we don't observe and transport a gap. But the correlations might remain there, and therefore the superconductor is still can be linked to the correlations in the system. So I think one cannot really disentangle superconductivity and correlations here. Of course, the other possibility is, which is also debated, was whether this could explain also in an electron phonon picture for the superconductivity. I think that would also be possible, but I think right now we're all leaning more still towards a correlation, unconventional type superconductivity picture. Well, of course, we don't know.
Because if I think very naively, if the interaction decreases, I think that maybe superconducting will also decrease, but it looks like it's not the case.
Right, I think that's what we thought in the beginning, honestly. So when we started this work, that we would maybe to see that TC changes proportionally to the strength of the insulator. But I think talking then later on to cuprate people, etc., I think I heard also arguments that you go basically from sort of a cuprate to more like from a cuprate to more like a pnictide sort of picture, because in the pnictides you don't need a insulator to be the parent state. It can be also like a correlated metal or so. As far I mean, but I think it's one of the central questions, to be honest, about the superconductivity here. So how does one can really explain it?
Dmitri, sorry. One question: at which temperature you kill the correlated insulator? And if
around usually 5 to 10 Kelvin.
And then you go to a correlated metal, or you go to a normal metallic state in the.
Right. I mean, this is again from transport. I don't think we can distinguish a correlated and non-correlated metal, right? So I think actually no. So I'm actually sorry. So I mean, there is right. So there's you're correct. So basically, we see. So there was this Pomeranchuk effect observed by several groups recently, right? And their claim is that isospin fluctuations are really strong up to like 100 Kelvin. However, insulators we form only below 10 Kelvin. So the correlations survive at much higher temperatures, but only the sort of sharp insulating transport features we observe below 10 Kelvin. Mm-hmm. So what I'm saying is also in this picture here, even though the insulators disappear, doesn't mean that the correlations are gone.
I also have a question. Does it matter? The superconducting dome, especially on the negative filling factor side, has shifted from it's almost shifted by 1 electron per cell. Does that matter at all? Or do you think it's just the same type of superconductivity?
Yeah, so somehow in twisted bilayer, we observed superconductors shifting back and forth. We don't know. I mean, our guess is some disorder-related thing potentially that kind of shifts the position of them, but we're not exactly sure. So it's for sure not this ideal picture that like in this case where you have like two superconducting domes sharply symmetric around the insulator position. It's typically a little more wildly spread. Yeah. It could be related to some sort of disorder. Actually, in this new mirror symmetric trilayer graphene, it seems to be a much more stable phase diagram. So usually, we also have some results now, but usually the phase diagrams which I've seen from colleagues, they're usually very robust. Whereas in twisted bilayer, they're kind of a little bit disordered, I would say.
Yeah, okay, good. I was going to ask another question about that, which is exactly that. If you took a different sample and looked at these same numbers that you're showing us, HBN thickness and twist angle, would you see the same phase diagram or not really?
Not necessarily, no, because yeah, okay. I mean, okay, so hitting exactly the same parameters is already pretty hard because, you know, we don't control these parameters right. Too well experimentally. But also what we know matters a lot is twist angle disorders, strain profiles, percolation paths. Because these superconductors are not homogeneous, there are also maybe some different percolation paths for these. So that's why actually we form Josephson junctions in devices where there are supposedly no Josephson junctions. So the systems are very disordered. So my guess is that this trilayer system is maybe a little bit more stable because somehow the extra layer of graphene, it kind of stabilizes these inhomogeneities. Mm-hmm, mm-hmm. But this is just a guess at this point. Mm-hmm. Okay, so I can move on from this part of the talk to topological properties. Okay, so I'll just do that. So and sort of another sort of aspect again about this system which excited everybody is that again we have strong correlations, we have superconductivity, but also as I will show in a second, we all are convinced now that we have also non-trivial topological properties. And I think if you talk to Ali Yazdani or so, they were really excited that they have now a topological system with interactions, because typically that's not really, that's a rather exotic combination as far as I understand. And so basically there were, as I mentioned in the introduction, so people define, if people look at sort of the winding numbers, so there were many groups, Oskar Raffeg, Andre Brennevik, Ashwin Vishnawan, who really looked at those properties in more details. They typically find that the billion zones have a non-zero helicity of +2 and -2 in the different billion zones. And this is very much different. This is very different from a single layer graphene case where the winding numbers is just 0. And therefore, it's impossible to find localized Wagner function from the system. And really what people are now using as sort of the ground state for the description of these bands are basically sort of churn bands. And basically, if one looks at different orbitals, depending on what kind of sublattice, belly, and spin this orbital has, one can define basically 4 bands with churn number of -1. And so basically, these are these combinations, and 4 bands of churn number +1. And really, in a normal situation, all these bands are, of course, perfectly degenerate. They have the same energy, and the total added up churn number is still 0, and then therefore no chance to observe this sort of underlying topology here. However, of course, in graphene, one can play tricks. One can try to induce gaps and to gap out these different churn bands. And for this, of course, one needs to break C2T symmetry one way or the other. And for example, the groups of David Goldhaber Gordon and Andrea Young, they broke C2 symmetry by aligning graphene to HBN. And the HBN substrate basically breaks the inversion symmetry on a single particle level. And of course, one can try to sort of break time reversal by applying the magnetic fields. And also, of course, another possibility is that interactions somehow break those symmetries by itself. And I will sort of talk along the lines of interaction broken C2T symmetry. And so basically the first experimental features which we started observing, and many other groups at the same time started observing too, is people started again applying perpendicular magnetic fields to somehow induce some sort of time reversal symmetry breaking in the system. And those were, again, prominently Ali Yazdani, Andrea Young, Eva Andre, Pablo Ferrero, who last summer observed very similar results. And really, the experimentally striking feature is that we observe churn insulators which originate from different filling factors per meridian itself. So, for example, here, these experimental features correspond to a sequence of churn insulators of churn number 4 starting from charge neutrality, churn number 3 starting from filling factor 1, and so on. So there's always a robust correspondence between churn number and filling factor. And the reason we kind of identify these type of experimental features as churn insulators is really that they follow this diagonal line in the B to N phase diagram, which is given by this Schroeder formula. And of course, we measure quantized conductance in the whole measurements, so we can really define a very robust churn number to each of those states. And basically, the reason we also distinguish these states from just Landau level quantization is because we also can extract the energy gaps in this problem. And usually the energy gaps are an order of magnitude larger than for typical Landau levels. Also, the quantization fields are usually an order of magnitude lower. And I will show also in a second that we also observe these states also at zero field. Basically, so let me move on. So basically, really, these states can also appear, as I mentioned, at zero field. So for example, in this particular device, which we had, so this is a device which is very comparable to all other devices I showed. It shows superconducting phases, it shows correlated insulators, but it also shows in zero field, centered around a filling factor 1, a very strong hysteresis loop if we measure RxY, depending on the magnetic field direction. So there's clearly some magnetic state which is formed around a filling factor 1. And this magnetic state is identified by the hysteresis loop, and it's almost quantized as well. So if you look at the RxY value, which we obtained here, it really has a almost quantized value of a Chern number 1. And basically, what we can really what we can also study in this type of situation is we can also study the phase transitions which are going on in magnetic fields. So because for this particular case here, as I mentioned, we observe a magnetic state with a Chern number of 1 at 0 field, but however we go to higher magnetic fields, we see that the state disappears, and we go over to a again to a Chern number of 3. So I'm sorry if I'm a little fast right now. So I noticed I'm a little bit went to a different topic, but let me just basically explain a little bit better what is the sort of theoretical picture which we are dealing with here. And so here I will just paraphrase sort of the work by our collaborator Andrei Bernovic, who has done careful theoretical analysis of the magnetic phase diagram in the system. And so basically what they're predicting is that just by taking time reversal symmetry breaking into consideration, which arises from interactions alone, they can really define a very complex phase diagram for a twisted bilayer graphene. And what they find is that really that at 0 magnetic field, the system is highly, there are a lot of competing states. So it's really hard to define which ground state wins. But in their scenario, they can find that really odd integer filling factors to 0 field are partially intervariably coherent states, which have a non-zero Chern numbers of plus or minus 1. So this is what they find. However, even integer filling factors like -2 and +2, they're intervally coherent states with Chern number 2. So this is sort of the ground state. However, magnetic field strongly couples to the Chern numbers here, and magnetic field couples strongest to the stronger Chern number. So each of these states kind of goes over to a belly polarized state with a maximal possible Chern number, and therefore at these higher fields we observe these belly polarized state. And really, this is going back to sort of our phase diagram here. This is really what we observe in our measurements. So really, at 0 field, we get these low Chern number states with Chern number 1, which are given by this type of sort of schematic where we assume a partially intervally coherent state. And then if we increase the magnetic field, then this couples strongest to the higher Chern numbers, and we obtain a belly polarized state with basically where one belly is different, is basically polarized with respect to the other, and therefore we also have really strong contribution of orbital paramagnetism in this problem. Okay, and with this, I think I'll try to slowly wrap up. So I think one thing I also want to mention is that these devices, they're also extremely interesting for future Josephson junction manipulations. So that these devices, which I just showed, they're really devices where you can tunably switch from superconducting to magnetic phases. So basically, you can gate tunably create now Josephson junctions between superconducting states and ferromagnetic and topological states. And in principle, I think we're quite excited to do experiments and to hybridize these states. And in principle, this is also having you potentially for Majorana fermion creation in the future. And with this, I think I want to slowly wrap up. I think I want to thank my group for their wonderful work, and I want to thank you for your attention.
Great, thanks, Dmitri. That was super interesting. Are there questions? And I also, maybe I can start with a question about what you were just talking about. Are there any signatures you can observe for these inter-valley coherent states, or is the main signature just watching the Chern number change?
Right. So I mean. So your question is whether what is experimental probe to test one of the versus the other?
Yeah.
Right. Yeah, that's a good question. So in transport, I think it's really hard to know. Probably in STM, maybe this is something which they can address in a better way, because they might potentially test different lattice sites. And to see whether there's some asymmetry between them. But right, in transport, we're not 100% sure how to do it. There was a paper by Jason Alexia, I think recently. They proposed to, in JJ experiments, to distinguish these states. But yeah, I have to read that paper a little bit more carefully. But in transport, in sort of this type of transport that I showed here, it's hard. It's actually very hard to do, I think.
Yeah, makes sense. Antoine, did you have a question?
Yes, I do have a question. I was intrigued to see, Dmitri, that on your last slide, you acknowledge Felix Baumberger. So is there any hope, or maybe already results doing photo emission on this device?
Right. Yeah, so I actually, this was one of my first slides. So we already did that with Felix.
I missed that one. Okay.
Right. So this is photo emission performed by Felix on our devices. So they were clearly able to resolve the flat bands. However, as you see, it's relatively blurry, right? So I think there are two challenges. So first of all, the devices are very small, and so it's hard for them to get a really good energy resolution. I think when I talk to Felix, the best possible energy resolution they can get is maybe 3 millielectron volts.
Yeah.
And the bandwidth here is 10 millielectron volts.
Yeah,
so then,
sure. It's very challenging. Yeah.
Yeah. So then getting like fine structure and interaction effects in the bandwidth, it's maybe extremely really pushing the limit there.
Yeah, but it's beautiful that this is coming up. It's great.
But it's also what's really also the sort of the Fermi surface reconstruction. They can get really a nice comparisons to the band structure calculations.
Okay, thank you.
I have another question, which is going a little bit beyond what you were talking about, but I was looking at your papers earlier. And my question is, this is all about the first magic angle, but you also looked a bit at the second magic angle, and I know that is a lot harder to access. So my question is, what do you see at the second magic angle? How does it compare to the first magic angle?
I mean, right. So when we started the work, we hoped to see interaction effects in the second magic angle as well. So we didn't see really smoking gun evidence of interactions. I think whatever we saw was secondary sort of comparisons. So actually, Andrei Bernovic, they did the calculations there, and really what our sort of features kind of matched best sort of an interaction model. However, it was not so striking as observing correlated insulators like in that magic and graphene case. So that's one thing. And then the other thing is, of course, all these topological properties, which I talked about, they're also true for these smaller twist angle devices. And there, what we were predominantly interested in the Hofstadter physics, because there were some predictions that also Hofstadter butterflies are distinct in these topological systems than as compared to normal systems. And the advantage of small twist angle graphene is that the unit cell is much bigger, and therefore you need a much smaller magnetic field to create a Hofstadter. So you get already a Hofstadter, full flux through the Hofstadter at very few Tesla. So that's what we studied. But I think I would say so. The topological properties are very similar to magic graphene, but all the interaction physics is not as well pronounced.
Yeah. How do you, is there a big fear of twist angle disorder at the very small angles?
Yeah, it's strain effects, lattice, so corrugation effects, etc., are in principle more pronounced in smaller twist angles. Also, of course, in a small twist angle, the lattice size is even larger, so therefore interactions are even, the electrons are further apart, so interactions are weaker in principle just by that argument. So I think honestly, if people want to enhance interactions, they kind of go rather, they want to rather increase the magic angle. They want to go to maybe a 2 degrees system where sort of the flat bands are formed at 2 degrees. Then the lattice constant is smaller, and then the interactions could be actually even stronger. And this is also the case in mirror symmetric trilayer.
Right.
Right. It has a twist magic angle of around 1.6 degrees. So in principle, this is going more the right direction there.
Are you guys looking at trilayer also?
Yeah, we have some. We also, yeah. It seems to be a more robust system. Maybe it's actually, but maybe it's also more complicated. So there must be some trade-off.
Yeah. Are there any other questions? Maybe I can ask another question then also, which is, what's the maximum number of layers that you're conceivably thinking about stacking, or is tri-layer the limit that's actually going to give you nice results with low disorder?
I think I was actually surprised how easy it is to make tri-layers. I think first of all, it's too hard to be true to make 2 layers. And then actually tri-layer was actually almost easier to make. So we're not too afraid to make 4 layers or 5 layers now. But I think what one needs to be careful about, I think there is still maybe a second Morée lattice, a larger Morée lattice formed between the bottom and the 3rd layer. And this type of disorder would just grow by when you add each layer. So it's not clear how far you can actually push all these ideas.
Yeah. Good.
Jen, can I ask a question?
Of course.
Sorry. So in the tri-layer, what's the... Hey.
Okay.
Sorry. Following you everywhere. What's the, in the tri-layer you were mentioning, so this is actually related to Jen's question also. You're mentioning it's more robust, but more complicated. So what's the angle disorder there? Is that the reason for robustness? It's a larger angle, right? The magic angle is larger by, I guess, √2 or something.
Right.
So do you have, I mean, you don't have access to know what the angle disorder is there, right?
Right. So you probably know of some STM experiments on the system.
I don't.
Yeah, right. So
He doesn't tell me anything.
right, okay. But so basically, I would say what is striking is that the different phase diagrams I've seen so far by the group of Philip Kim, by Pablo's group, also comparing the results to our group, the phase diagrams look almost identical. And even though the twist angles were not exactly the same. So somehow, and this is in contrast to a twisted bilayer where I mentioned, so somehow the phase diagrams look always different. This was kind of shocking to see. So somehow there is something about that system which is a little bit more robust. The phase diagrams at least come out the same way.
So what angles are you looking at?
1.57 or so, yeah, we're very close to Pablo's results. And I think also in their case, I think they have several devices now measured out, but I think in their case, it's also seems to be, the phase diagram seems to be a little more robust. However, I also heard of STM experiments, I think, where really it's not true. So the top layer and the bottom layer and the top layer, they are supposed to be AA stack, right? They're supposed to be perfectly AA stack. And that is, that would be fantastic if that would be true, because then somehow these top and bottom layer destabilize each other. But apparently that's not exactly true. So there is a different twist angle between each layer. I
see.
So I don't know what to do about this information at this point.
Okay, thanks.
Yeah.